Okay, good morning, everybody. So let's start with the second lecture on electrical pulses in the brain. So today, in the grand finale, we will look at the mechanisms behind the action potential, so the generation and the propagation of the action potential. So these are the two guys, Sir Alan Hodgkin and Andrew Huxley, who discovered all this already quite some time ago. So they were awarded the Nobel Prize. So this was before even computers existed. So all the computations that they did, because they made a mathematical model actually to describe in great detail the shape of the action potential, was all done by hand. So it was really magnificent work in the sense that they not only could describe the shape of the action potential in great detail, but they could also predict, based on their measurements, the existence of ion channels, which were only discovered several decades later. So it was really a truly magnificent piece of work. And also, I think it's worthwhile to mention that the model that they developed, which was of course called the Hodgkin model, is still used today without any changes actually. So if you look at maybe you heard of the Human Brain Project, so that's a big project, was awarded 10 years ago by the EU. It was 1 billion euros, was the largest scientific grant ever awarded in Europe, to build a simulation of the human brain. And they're still using supercomputers nowadays, of course, simulating millions of neurons in a computer simulation. But they're still using the same formalism that was discovered by Hodgkin and Huxley to describe the exponential, the propagation of the exponential in the brain. So I think that's quite remarkable. So before we go into the details, maybe a short recap of what we discussed before as the basics. So, like I said in the previous lecture, all the elements, the biological elements that are needed to produce these electrical signals are this membrane which isolates, let's say, inside from outside. There's no charges that can flow through the membrane. And these charges can only, so the ions, sodium, potassium, which are the main ions that carry electrical signals in the brain, they can only flow through these proteins, these ion channels. And these are selective for these ions. It's not all the ions can flow through all the ion channels. There are selective ion channels which only selectively can conduct one particular type of ion. Again, that was not known at the time that Hodgkin and Huxley were doing their research, and we're trying to understand the mechanisms behind the action potential. We'll come to that in a minute, how they discovered this. And then the important thing is that based on diffusion and electrical repulsion and attraction of forces, electrical forces, you have the situation that if you have a difference in ion concentrations inside and outside, and remember that this was established by these ion pumps, and it takes a lot of energy to maintain those gradients, and to pump ions from inside to outside and vice versa, to maintain this gradient. That's where all the energy goes. And then if you have a membrane, like we have here, you have inside, outside, you have different concentrations, then what will happen if you have some channels that are selectively conducting, in this case, potassium ions, they will diffuse to the other side and you will start to build up a potential. And that potential will generate electrical force that will push the ions back. So you have a force, diffusion force this way, but you have an electrical force this way, and at some point, at a certain potential, there's an equilibrium between the diffusion force and the electrical force. That's the electrochemical equilibrium, and that's also where you have the reverse potential, or the equilibrium potential for that particular ion. In this case, we calculated there's this Nernst equation that you can use, depending on the logarithm of the inside over the outside. That's a prefactor. But you can calculate the potential that you arrive at, in this case it's minus 58 millivolts for this particular concentration. Okay, so that's one part. Now if you have not only potassium but also sodium, and you have potassium and sodium channels, it becomes a little bit more complicated. So also the equation that we need to describe all the contributions of the different ions and their concentrations to the resting membrane potential is given by this Goldman equation for monovalent ions as described here. And so basically it is an extension of the Nernst equation, but now with several ions in there, and also the permeabilities of the ions. And that is very important. What is the permeability? That is actually how well these ion channels conduct the particular currents. And the important thing is that, of course, these permeabilities we will see, they can change. So these ion channels don't have a fixed conductivity, but they can open and close, basically. That's the opening and closing of the channels. And we will see in the rest of the lecture how that works and how that plays a role. But that is important. So, we already briefly discussed some extreme situations. So, for instance, and that is the base actually for the exponential. Like I said, these permeabilities, they are not constant, they can change over time. And the idea is that at rest, it's mainly potassium channels that are open. And their conductivity is much stronger than for the other channels. That's for this particular situation, if you're here. The permeability for potassium is much larger than for sodium. That means that you can actually neglect the sodium terms here. You can put that to 0 compared to permeability here. That means that you can just erase those terms from this equation and you end up with this equation only. And this is again, because then you can divide the numerator and the denominator, you can divide out the permeability. And you end up again with the Nernst equation, which gives you the reverse potential for potassium. So at rest, the resting membrane potential, as we call it, is close to the reverse potential of potassium because of this. Yeah? And then what happens, by some mechanism that we will discuss in a minute, if there's some depolarization, sodium channels will be activated, and that makes it that these channels become rapidly highly permeable and much more permeable than the other channels, the potassium channels and the chloride channels. So that means again that you can now neglect these terms here and here, and you end up with only these terms in the Goldman equation. And again, you can then divide out this permeability for sodium, because in the numerator and denominator it's the same permeability, and you end up with the Nernst equation again. So now the resting membrane potential is close, or will get close to the reverse potential for sodium. So that's here, okay? That also means that the exponential always moves between these extreme values, let's say, which are the reverse potentials for pure sodium and pure potassium. Okay? So the only thing actually now that we need to understand the mechanism for the exponential is how these channels open and close, and what's the dynamics and what is driving these channels. Yeah? And the interplay. So that's what was in a nutshell what we discussed in the previous lecture, and now we will build on this in this lecture. So the important thing is that we, in order to describe, let's say, how these ion channels open and close, we first need to find a way to measure this. Okay? And that was the other big contribution that these two scientists actually made to the field. They were the first to design very elegant experiments to do this in a very controlled manner, to see if they could measure the currents. And I think both of them were physicists, so they had an entirely different look at solving this problem, right? So they were looking at as if it would be a electronic circuitry. And so they're not so interested per se in trying to provide biologically realistic inputs to the system, or triggers. They were interested in providing stimuli that were very simple, so that the response would also be relatively simple, so they would be able to understand the relation between the input that they gave and the response. And by that they hoped that they would be able to understand, the mechanism, and then from that they could see what happens in a more biological situation. And for that they designed this device, or this setup, where they could do electrical measurements. So we discussed that they chose this giant axle because of accessibility. It's a 1 millimeter diameter wide axon that they cut out of the squid. And then they could actually wash out the interstellar solution with a needle. With a syringe, they could put in certain solutions of interest, so they could manipulate the interstellar solution and the bath solution, of course. That they could change the ion concentrations to whatever they wanted it to be. And then they could stick in electrodes, one to stimulate the system, to provide currents into the system, and the other one is to record the potential. And this is always with reference to a reference electrode in the bath, because a potential is always a potential difference, okay? Measuring inside from outside. So that's also how the membrane potential is defined, inside versus outside. So with these 3 electrodes and a very intricate electronic system, they could actually stimulate and record at the same time and see how a axon responded to, for instance, current stimulation. But also, because of this very clever electronic system, they could also provide current in a way that they could maintain the voltage at a certain point and then measure how much current they had to inject. And that was actually the current running through the system. So with that same system, they could also do current recordings. And therefore, we distinguish the 2 types of recordings that they could make. They could clamp the voltage, that they could determine at what voltage the system was held by the stimulation system. And then they could record the currents that were generated by the system as a response. So voltage clamp measurements, typically you provide a certain voltage profile and then you measure the currents that are induced by this. And the other type of measurements that they could do was current clamp, where they injected a certain current, and they could measure the voltage responses in response to this current stimulation. Okay? So that's very important. Are there any questions so far? Maybe things that popped up? And looking back at the previous lecture, looking at the slides. No? Okay, great. So, they were the first to have a very good recording of the exponential. And it's important to distinguish some, and that's what they also did, some particular features of this exponential. So first of all, and it's not so clear here, there's this kind of threshold, right? Remember that they had this active pulses and this passive pulses, electrical pulses. So if you depolarize the membrane strong enough, then at some point it will reach the threshold, and then you get this very rapid, what we call the rising phase of the exponential. And then it goes from minus 60 or so, all the way up to even to plus 30 millivolts. This is what we call the overshoot, because it's actually now going to positive membrane potentials. Okay? So remember that the resting membrane potential is always negative. But then rapidly after reaching this peak, it also has this very steep falling phase, which is, for instance, different from what we see with synaptic signaling, where you have also a relatively fast rise phase, but then a very slow decay. In this case, you have a very fast decay phase also. And then after that, you actually have what we call the undershoot phase. So it goes actually below the resting membrane potential before it bounces back bounces back to the resting membrane potential. This is a relatively slow recovery to the resting membrane potential. Okay, so these are the important features of an exponential. So it's quite interesting because it's not a very simple, trivial signal, right? It has quite some specific features. And still they took up the task to see if they could understand every little detail of this exponential. Okay. So they started out with doing this voltage clamp measurements to see how the currents, so to identify basically what currents were carrying the exponential, what currents were there actually, and how they responded to changes in voltage. Okay, so there was a lot of research done before, and people knew that there were currents, they knew which ions were involved. Of course, you could measure the potentials, but they didn't have a good understanding how these currents related to the voltage changes. So like I said, they took a very systematic approach and starting out to give very simple stimuli to this axon. And the first thing they did is starting to do these voltage clamp measurements where they applied very simple step pulses, going from minus 65 for instance, in this case to a hyperpolarization pulse, in this case of minus 65 millivolts, and look at the currents as a response. And in this case actually it's a very simple response in a way. So when you make the step, you have this peak, this is a capacitive current, but then not much happens. So this capacitive current is basically when you have a simple capacitor, so that the membrane actually acts as a capacitor, and a capacitor is also in physics or in electronics, it's a unit, electrical unit, where you can store charge. So there's a certain, if you have a certain potential, there's a certain amount of charge that you can store on the capacitor. It's very important, for instance, for computer systems. And it's also how the membrane acts. And if you hyperpolarize the membrane or depolarize the membrane, you have a redistribution of these charges on this capacitor. And it takes some time for these charges to redistribute, and that provides this current. That's called the capacitive current. So you don't have to know the details, but this is just to give you a brief idea of what this capacitive current means. There's a quick redistribution of the charge during this hyperpolarization. But once it's at equilibrium, there's no current flowing anymore. Okay? So this is not what is carrying the exponential. And this happens even if you have a membrane, for instance, without any channels. You still have this redistribution of charge. Okay. But now the interesting thing is, when they gave the same pulse, but then with a positive sign, so a depolarization of 65 millivolts, then a lot of things happened. So again, we recognize the capacitive current, which is logical because it's now you give the pulse in the other direction, so you also have this redistribution of the charges in the other direction, giving a current in the other direction. But just neglect this part now and look at what happens here. So can anyone describe what you see? So you always have to think, at least I like to think about this, so this is what they saw. They didn't know what it meant. So in that sense you have the same sensation you could have as they had when they measured it for the first time. So what does it mean? What do I see? Can I understand? So you give a very simple, very rapid depolarization, and then you look at the currents that you induce in the system, and you see these. Maybe just first start with a description of what we see, without trying to understand. Anyone? What are the features? Still early? Remember, it's already too difficult. But actually, I think it's described here. Maybe that's why you were kind of hesitant to state the obvious. But the other interesting thing is that you have this two phases of the response. First, you have this what we call an inward current, and it's just a definition, but it's a negative deflection of the current, or negative current, and then it goes into a outward current, or in a positive current. Okay, and this is transient, and this maintains. As long as we maintain the pulse, this current maintains. Okay? And keep this in mind, because now what they did, they actually start to apply different amplitudes of this voltage stimulation. And then this happens. And now I really need your feedback to observe what they observed. So if you apply different depolarizing pulses, there's a lot going on. So what do you see? Anyone? So maybe start with the simplest question. So does it scale? So meaning that if I apply, let's say, a pulse that is twice as high, is the current signal, does it have the same shape? It is just multiplied by 2, or is that not the case? Meaning that's a linear effect that you see, or is it non-linear? Who think it's a linear effect? Who thinks it's a non-linear effect? Okay, so it's the majority. Yeah, indeed, it's non-linear, right? Why is it non-linear? Anyone? Ah, come on. Okay, should I? Yeah. Yes, exactly. Yeah, but it disappears. Yeah. So that's the main observation I think to make here. So this outward current is quite linear, you could say maybe, although it's not entirely linear. But indeed, this peak here, it starts with this weak depolarization. You already have quite pronounced hyperpolarization, and then. Or a negative current, I have to say, it's not hyperpolarization, but negative current. That becomes even larger if you go to stronger depolarization, which maybe makes sense. But then, if you go to even stronger stimulation, it starts to weaken again, to reduce, and actually to disappear. And at some point, it seems actually that it's flipping sign. Okay? So that is definitely not linear. So what is, if you see this, what could be one conclusion? Yes. Say again? There? Threshold value. Why do you think so? Yes, but it will be a difficult threshold value because it will be for certain depolarizations you get a signal, but then beyond certain, and it becomes stronger. So if you pass the threshold even further, you get a stronger signal. But then if you go even beyond that, then it starts to weaken again. So it will be a highly nonlinear threshold. So that's not actually what Hodgkin took out of this. But they thought maybe these are two processes basically. So we're looking at two currents. So this is a separate current from this one, and they're responding to voltage in a different way. Okay? Yeah, so they plotted actually the peak here as a function of the depolarization step, So this is the depolarization step, and then they plot the peak. Yeah, so you see the membrane current, so they plot the peak current here. And they did it for the peak here, so the steady state value for this part as well. And then you see that this is the late current, this is the early current, it has a different voltage dependency. Okay? And from that they concluded, we think that there are maybe two processes going on at the same time, maybe carried by two different ions. Okay? Yeah, so what experiment can we do to show that there are at least two different currents in the squid axon? And the hint is that Hodgkin actually already knew that ionic currents were carried by sodium, potassium, and chloride ions. And so they did first these voltage clamp experiments. They noticed that there were probably two processes, and now they want to prove this. What is an experiment that you can think of to show that there are two currents, two different currents operating at the same time? Yes? Toxins, yes, very good. And that's exactly how we do it right now. The point is, at that time they didn't know that these toxins were acting on these channels, because the channels were not discovered yet. But that's a very good point. So that's one way of doing it actually. And that's how we do it now in nowadays modern neuroscience. But there's another way. Anyone? Okay. So what? Remember that they could manipulate the solutions. Eh? They could choose any solutions that solutions for both for the outside and for the inside that they wanted. So they could create their own ion concentrations, whatever. So with this, they could make selective solutions. So, for instance, leave out the sodium and see what happens. And that's exactly what they did. So, if you go to sodium-free or potassium-free medium, then this is what they see. So here they have extremely high sodium. They have this pronounced peak here. This is all for the same depolarization step. Now they keep the depolarization the same, but they're changing the solution. Okay? And I think here they change the extracellular solution. Yes, that makes sense, right? Yeah, makes it easier to change. And then they go to sodium-free solution, and then this component is entirely gone. Yeah? And then if they wash in again high sodium, then you get back this component. So with this, and notice that the other current, so the positive current doesn't change. Yeah? So this really shows that this particular component was carried by sodium and sodium only. Okay, they could do the same for potassium, and nowadays, like you mentioned, we can use toxins. So here again is another proof. If you block the sodium channels, you get rid of this component, but you can also block the potassium current and you get rid of this component, so the depolarizing current. Positive current, and you are only left over this component. Okay, so this is excellent because now they could not only show that potassium and sodium were carrying these currents, that they were separate processes. They could also now investigate these currents in isolation. And that was the next step. Because now they were thinking already, okay, how can it be that we have separate currents that are operated in a different way? And they predicted actually there should be some selective, I don't even think they called it at the time channels, but some selective permeabilities in the membrane that are selective for a specific ion. Yes. And I think this is just a side step to notice that, to show you that much later, Sackman and Neuro, they also got a Nobel Prize for this type of research. They were able to show actually that ion channels existed. And they did this with a very clever technique, and that's the technique that we're still using, actually in my lab also. It's called the patch clamp technique. It's called patch clamp because you take a small glass pipette and you isolate, this is a neuron, and you isolate this very small patch of the membrane. And the smaller your pipette tip is, as you can see here, the smaller piece of membrane you can isolate. And then in some cases you can end up with a situation where you have a single ion channel in your pipette. And then somewhere here, there's a big electrode where you can measure the currents that are flowing only through this small patch of membrane. And if there's a single ion channel, you're picking up basically the current of a single ion channel. Okay. So the trick was, and he was a physicist trying to find the right glass, let's say, to make this pipette, because it has to seal very well with the membrane. The membrane has to stick very well to this glass pipette. So you also apply a little bit of suction. You actually do that by mouth. So we have a hose connected to this. That mouth is still the most sensitive way to apply enough suction to have enough membrane inside the membrane, inside the pipette that seals to the wall of the pipette. And that is necessary because you should prevent at all costs that there's leak current flowing from the reference electrode directly here into the measuring electrode, right? So they put a lot of effort to make this proper seals called giga-ohm seals, and then they could have these noise-free recordings that were good enough to pick up this very tiny, small current through the ion channels. Okay. And later on, they discovered by accident actually that if the seal breaks open, then you can actually record all the currents from the whole cell. And that's a whole cell recording. And then in one go, you can measure, let's say, all the ion channels that are on the membrane at once. Gives you also much better signal-to-noise ratio. Okay. So, if you make such a recording, then this is what we measure actually. So what do we see? Anyone? So again, this is a depolarization that we give to the cell, and then this is what we measure in the pipette. So we see this small current deviations, and this is current that we measure. But I think the important thing is to know two things. It's always the same amplitude, but it's also stochastic, as we call it. So it's not, so I have to say this is for different depolarization steps that we give. Different sweeps or different trials that we do, right? So we give a depolarization, then we record this current, and then we go back to -100, and then we do it again, get the step here, and then this is the response. And on average, it kind of gives the same response, but it's stochastic. It's never identical. So there's a chance process involved. And if you kind of average all the signals out, this is something that you get. This is what you get basically. And that's also reminiscent of what we do if we record all the ion channels in the cell at the same time, right? And this is actually this positive current, this delayed outward current that we were measuring previously, right? So there's maybe some other thing that you notice, that this is a step that you give, but the response always looks like this. It has some exponential time constant that needs to arrive at the new, let's say, equilibrium current, okay? So it takes some time. And the way they interpreted this was that there's this channel, and that can be in the closed or in the open state, and when it's in the open state, it conducts these ions. So if you have a single ion channel, this is a stochastic process, right? But you increase the chance of opening by depolarizing the membrane. And it has to do with that there are these sensors in the protein that can sense charge, and if you depolarize, the chance of going to the open state is increased. But it's a stochastic process, that's why you see this stochastic opening here. Because it's an ion channel, it can only be in the open or closed state. There's not like such a thing like a half open state or whatever. it's always the same amplitude. It's either closed or open. Okay? And then you see that the probability of being open in the open state increases over time. So it takes some time to develop that chance to be in the open state. And then if you would have a lot of these ion channels on the membrane, it averages out to a signal like this. And then if you hyperpolarize the membrane, the channel shuts down again. Okay? Is this clear? Okay, great. Now we do the same thing for sodium current. So then we make we either block the potassium channels or we make a sodium selective solution, and we do the same type of recording. And now it looks like this. And now I really want some input from you guys. What is different from what we saw with the potassium channels? Just describe what you see, what you think is different. There are many things I think that are different. What is the most obvious thing maybe to notice? Yes? Yes, so the length, you mean, the opening time is different. Yeah, it's definitely different from what we saw before, right? But they also seem to vary a little bit more from trial to trial. Yes, one other thing? Yes. Yes, exactly. Very important. You go in the other direction. This was a positive current, this is a negative current. Oh. Yeah, okay. And one final thing, very important, a little bit related to what you said already, but yes, it's shorter, yeah, and that means actually that they close already during the pulse. So that's very important, very remarkable actually, right? So these channels, they are activated, they open, but the stimulation stays the same, but then they close again already during the pulse. So remember that the potassium channels, they only close when you hyperpolarize the membrane again. Okay, then they start to close up. Not for the sodium channels. Okay, and if you average this, you get something like this. And of course, if you make the whole cell recording, it has the same shape. It's the sodium current only. It's this downward reflection that we noticed from the beginning. Yes? Say again? This. That is the capacitance peak again. Yeah. So you can neglect this for now. Every time you give a depolarization, you always get a negative peak. If you give a depolarization, you get a positive peak. I don't know why they didn't show it here, actually. I think it's just a mistake. Okay. So now what is the interpretation of this signal? That's very important. So this is the sodium channel. Actually, it looks quite similar to the potassium channel. That's because of evolution. They all have the same origin. There was one prototype channel that evolved during evolution into different channels. Actually with different selectivity filters and also with different sensor mechanisms. So and that's, well, I will discuss it in the next hour, but you have this different ways of activating the channels, but they all conduct the ions in the same way. Again, opening and closing, but now we have two mechanisms. That's important. So we have the same thing, that's exactly the same, similar voltage sensor as we had for the potassium channels. So it will also open during depolarization because of this voltage sensors. It's stochastic again, of course. Now because the sodium concentration outside is higher than inside, as we saw in the previous lecture, this will actually lead to a depolarizing current, right? Positive charges will flow into the cell. But now the thing is there's an extra mechanism, and that is different from the opening and closing of the channel through conformational change. There is this extension here at the bottom, which also contains a charge actually, that can close the channel upon depolarization. and that's called inactivation. And the important thing is that this is much slower process than this. Why is it important that this is slower? Anyone? So what would happen if this process of closing would be faster than the opening during a depolarization? Yes? No current, exactly. Because the channel would close already before it could open during depolarization. So in order to conduct any current, you first, this opening through this mechanism should be faster than the closing later through this inactivation mechanism. Right? And that is exactly what you see here. It opens, but then it closes up again. And that's also depicted here. First opens, then closes. Okay? And it's a very important property, as we will see later. Yeah, so what I just discussed. This is called activation gate, and this is the inactivation gate. Yeah, and the important thing is, and already, I say disclose or the answer to a question that I have later on the refractory period is that once the channels are closed through this inactivation process, it also takes some time to recover from this inactivation, to have this gate going from inactivated to open again. So you need to have de-inactivation, it's called, and this is a slow process again. So if you go to the resting membrane potential again, it takes some time before these channels are open. So there's a short period where if you would then briefly after this depolarization and then go to hyperpolarization, depolarize again, then indeed you have the situation where these channels are still closed, so there's no current flowing through the channel, although you depolarize the cell. And it takes some time before the cells recover from this, before you can have again sodium flowing through these channels. Yes? Yeah, well that's what we come to later. Actually they contribute to the action potential. So remember that you have these permeabilities of sodium and potassium. The channels that we are discussing right now, these are the permeabilities for sodium and potassium. So what we are doing, and what Hodgkin actually did during these experiments, they were actually measuring the voltage sensitivity of these permeabilities. And then what you start to see that there's a kind of a feedback loop, right? So these channels, they are sensitive to voltage. Because of opening, they will change the permeability. That will also affect the membrane potential. And that will actually then also even depolarize more the cell and therefore activate more of these channels. So you get this positive feedback. And that's actually the mechanism behind the action potential. Now you already disclosed the whole clue of the rest of the presentation, but it doesn't matter. That's indeed what's going on. Alright, any questions on this? Because then we take a short break. Yes?
What's the peak at 50 milliseconds of the picture D?
Can you speak up?
In the last picture, what's the peak at 50 milliseconds?
The last picture.
On D.
This peak?
Yeah.
Yeah, again, that is the capacitive current. So for every, remember at the beginning, if you have, even if you have a membrane without any channels, and you give this type of stimulation, so fast depolarization or fast hyperpolarization, and you always get this capacitive currents. And I think they were wrong by not drawing it here because there should be a positive capacitive current as well. The only thing is that sometimes this appears to be smaller because you have this very rapid downward current that some of the capacitive current is cancelled by this rapid downward current here, but these are details. So for the understanding of this mechanism, you can just discard this peak. Yeah, but they just do it for accuracy. Are there other questions? If not, then we'll take a break and we continue at 10. Okay?